Hey, this is Mr. A, and I want to talk today about free body diagrams. They're real important when we solve problems in physics. Free body diagram it's a model, just like a lot of things that we use in science that we use to explain and predict with. A free body diagram, it's a type of model which represents the forces acting on a physical object. Okay, let me give you some examples. All right. One of the things that we've talked about already when I was trying to explain what a force is was I was trying to get you to see that if you tried to make this book move, you had to either push or pull it, right? So a force is a push or a pull, all right? Well, there are forces acting on this book even though the book is sitting still. One of those forces is the force of gravity, which is pulling it down. And the other force is the table pushing up on the book. So let me, I've represented the book now as just the little dot here. And then I'm representing this force down. This is the force of the book on the table. And then the force going up is the force of the table on the book. And I've drawn these forces equal. I tried to make them equal. My one might be a little bit longer than the other one. But I tried to make them equal because the force of the table on the book and the force of the book on the table are equal because the book isn't moving. When one is not winning, there's nobody winning the tug of war here. So that's what this free body diagram of the book on the table shows, is that the book isn't moving because the forces are equal to each other and they're zero. Okay? Let's take another example. Ball on string. Okay, here's a ball, and here's a string. Okay, yeah, that looks a little bit better. Okay. There is, can you identify the forces on this ball? Sometimes it helps if you, and they mention this in the book, if you like draw a circle around the object, and then you see what touches the circle. Well, one thing that's touching the circle is the string, right? Right, so if I represent now the ball as just a little dot, there is definitely something holding up the ball, and that is the tension on the string. That's what we call a contact force. Now there's another force on this ball, and we can't see it right here, but we know it's there because there's gravity. There's another force, which I'm going to write as mg, and that is the force that's equal to the mass of the object times the acceleration of gravity. All right. Now, if this ball is just sitting there, then those forces have to be equal. Right? Right. So this brings up another good point, is that this tension is a contact force, and this non-contact force is something that we call a field force. F-I-E-L-D force. So there's all types of There's all types of forces, but they can generally be broken down into contact forces where there's something tangible, in this case a string hanging off the ball, and then there are field forces that are acting at a distance. Okay, there are all kinds of forces listed on page 94 on the table. Okay, for you to check out. All right. I found this on the internet, and I think that this is, hope that you can read this. I just Googled free body diagrams on the images, Google Images, and maybe you can't see this too well, but this is helpful. What this does is to, like we did, you draw a circle around the object in question, and you try to identify all the forces on the object. That's step one. Step two, I didn't do this step, maybe we'll do it next time. It says draw a coordinate system. So they drew basically saying that y is positive, up is positive. And then the next step was to represent the object with a little dot, and we did that. The next step was to draw the vectors to identify the forces and try to make the size of the arrows proportional to the sizes of the forces. And this last step here, we haven't done yet, but we'll get there, is draw and label the net force beside the diagram. We'll talk about net force in a minute. All the examples that we've had is that there was a zero net force, right? So the mass was either at rest or at a constant velocity. Okay, but I wanted to show you that because there's just, oodles of good information out there on the internet. Let's take another example, free fall. Okay, I don't like my little pieces of paper, so here we go. Remember we had the example of the brick being thrown out the window, right? So a brick thrown out the window and it's falling. Okay. Here we don't have a table supporting it and we don't have a string supporting it. The brick is falling. So can you imagine, think about, tell me what forces are on the brick? Are there any contact forces? No. Are there any field forces? Yes. We have the force of gravity. Okay. Gravity is pulling on this brick. So without any resistance, if we forget about air resistance for right now, do you think this brick is going to accelerate? Well, yeah, that's what bricks do. They go faster and faster and faster as they drop into the air. We've worked a lot of problems on that. So yes. So this is the free body diagram for a brick falling through the air without any air resistance. Now, so free body diagram for an object in free fall. Now let's add with air resistance. Okay. Which direction do you think the air resistance is going to go? It's going to go this way. Right? It's not going to be as big as gravity at this point. I'm representing it as a smaller vector than the force vector that's pulling it down. So we do have a net force. Okay, and in this case, the net force is going to equal the acceleration due to gravity, the force of the acceleration due to gravity, minus the air resistance, the force of the air resistance. All right. So it's helpful now to subtract this vector from this vector and then your resultant, like we talked about before, is a smaller vector, but it still exists in the downward direction. So this is the free body diagram, and this is the resultant. Okay? All right. I threw this little definition in there. Maybe you ought to write this down in your notes. The vector sum of all the forces acting on an object is the net force. The vector sum of all the forces acting on an object is the net force. Okay. All right. Now let's get a little crazy and let's look at a simple, I don't like my little pieces of paper, do you? I don't. Let's look at a simple net force problem. Okay. I'm going to have to use my drawing. You see this? What I've got is a pulley, and off of it I've got two weights. One of them is a smaller weight, one of them is a larger weight. Okay. If we draw a free body diagram for this mass right here, we are going to have the force of gravity pulling it this way, and then we'll have the tension on the rope pulling it this way. All right, so the tension is equal to the force of the acceleration of gravity considering this smaller mass. So I've got a big mass and I've got a small mass. Now what do you think is going to happen? Is the little mass going to go up, or is the little mass, or is the big mass going to come down, or is it going to go up, or is it going to sit still? Well, I think you can see intuitively that if you have a free body diagram shown with the forces drawn proportionally, represented as vectors and drawn proportionally, this one is bigger than that one. So the resultant is going to be a force this way. And if you knew numerically what these forces were, then you could just say, you could subtract F1 from F2, and then you would actually get what that net result was. Okay. So this is where I expect you to be able to solve some of these problems, and we'll provide some more details for these problems. But I think just intuitively, if you are able to draw free body diagrams, you can predict what the answers are going to be. You don't know quantitatively what the answer is going to be until you plug in some numbers here. But I think that's coming. Anyway, so looking forward to doing lots of these kind of problems. Are you a little worried? I don't know. Remember, the main thing today was to talk about free body diagrams, right? And if you need help, I want you to Google Glencoe, that's the publisher of our textbook, Glencoe Animation Free Body Diagrams. And that will take you to a website where they will explain slowly and in great detail how to draw the free body diagram.